Welcome students. Today we will discuss about differential evolution algorithm. Differential evolution algorithm. In short, you can write as DE. Differential algorithm is also belonging to evolutionary computation algorithm. That means computation algorithm used for optimization. That means here for each iteration you will generate a set of candidate solutions. For each iteration you will generate a better solution from the previous solutions. Okay. The specialty in differential evolution algorithm is it can perform over continuous domains. The main advantage of differential evolution algorithm over genetic algorithm is it can perform over continuous domains. Okay, that means even if a variable can take real numbers, we can perform differential evolution optimization algorithms. That means in differential evolution algorithm, each variable value can be represented by a real number. In previous video we have discussed genetic algorithm where each solution is represented in the form of a binary vector. Here we can represent the binary solution in terms of a real number. Okay, that is a specialty in this. So here also, just like genetic algorithm, in DE algorithm, differential evolution algorithm, we are having mutation and crossover operators. But in differential algorithm, mutation is performed with the help of arithmetic operations in the form of multiplication or subtraction. We can perform mutation operation. Similarly, just like in genetic algorithm, here also we will perform crossover operator. Okay, crossover operation to generate new set of population. So we will see how mutation is performed, how crossover is performed in DE algorithm. We will take one example and we will illustrate in the coming slides. So first of all, we will first understand what are the steps involved in differential evolution algorithm. Okay, what are the main steps involved in this algorithm? Main steps involved in differential evolution algorithm. Let us see one by one. In first step, first of all, choose the target vector. First step is choose the target vector. Let us denote as xt. Second thing is So here these are the steps you have to follow for generating a new population. Okay, in our previous video we have discussed the generation of new population from old population. Here also we have to generate new population from the old population. Okay, the initial population is generated with the help of some random initialization. Okay, so let us see the process or steps involved in generating new population in differential evolution algorithm. First step is choose the target vector. Let us denote as xt. Second one is randomly choose two population members. Let us denote xa and xb. You need to understand that x is a solution vector. Okay, you can write x is a solution vector in a current population. Okay, so xa, xb. Third step is build weighted difference vector. Of xa and xb. That means you have to compute the weighted difference vector. So that means you first perform the difference between xa and xb, xa and xb, and multiply by some weight. Generally we will call it as a scaling vector. Okay, so you can see f, we will call it as scaling factor or weighting factor. F is a scaling, or you can say as a some weight. Generally the value is in between 0.5 to 1. So that means here in this algorithm f is a hyperparameter. Okay, f is a hyperparameter. So that is the third step you have to do. Third step is build a weighted difference vector between xa and xb. The fourth step, you need to add this weighted difference vector with a third randomly chosen vector. So therefore add, I will write choose randomly third solution vector. Here vector means solution vector. Let us say xc, and add it to the weighted difference vector. Okay, so that means the output what we got in step 3 you should be added to xc, weighted difference vector. So that means what you do means you have to perform something like this. xc plus f into xa minus xb. So that is the step 4. In step 5, perform the crossover. That means perform crossover operation between step 3 output of step 3 vector and the target vector xt target vector which is there in the first step. You have to perform the crossover to get trail vector, let us denote x trail. So that means the output of step 5 is you will get x trail. Okay. Perform crossover operation between step 3 vector a small modification, step 4 vector you need to perform, step 4 vector and the target vector to get trail vector. Okay, so once you got it, you compare the fitness value of trail vector and the target vector. That means f of xt and f of x trail. Okay. Based on this comparison, choose the best vector and store it in new population. So new population P new. So what you have to do means, we have done a very simple process. You have to take a target vector in old population, we name it as a xt, and then in second step you have to choose two random vectors in old population or current population, xa, xb, perform weighted difference between these two vectors and add to the third randomly chosen vector, let us see xc, and perform the crossover operation with target vector to get your trail vector, and finally compare the fitness value between x trail and x target vector to choose the best vector. After choosing the best vector, you have to store it in the new population. So these are the steps that are involved in this. So let us, after understanding this statement, these steps, let us take one example so that you will understand in a better way. So once after understanding the example, we will write the actual algorithm in a better way. Let us write the example. Our objective function is to find the minimization of f of x. Okay, we are taking a simple function x1, x2, x3, x1, x2, x3. Let us suppose the range of x1, x2, x3, they are all in between 0 to 1. Our aim is to find the minimization for f of x. let us see how our differential evolution algorithm operates. So basing on the previous steps, we will try to illustrate with an example, and let us define the population size. Okay, let us define the population size, that means number of solution vectors in a population. Let us define as the population size NP, population size as 6, and here in this case 3 variables are involved, so the length of a solution vector is 3, x1, x2, x3, so D is 3 actually. The dimensionality of the solution vector is 3 here. So let us write the population. First population, I already told you, you can take any uniform distribution function and draw samples between 0 to 1 and fill the initial population. Initial population, let us denote P0, and in this population we will get x1, x2, x3, and I already told you the population size is 6, so you can tell as P1. Okay, for difference you can write something like this: individual 1. This is the first solution vector, or I can tell as something like this. Let us denote as solution vector S1, 0.68. You can draw random samples. Let us draw another solution in the population P0, 0.92, 0.92. You can draw any number of samples. Here we have told that population size is 6. Let us draw the samples and fill the initial population. I am randomly taking the values. This is a solution for 0.12, 0.9. These are all randomly taken values. 0.40, 0.81, 0.83, 0.94, 0.63, 0.13. So I hope it is understandable. So this is the initial population we have chosen. And the next thing is calculation of weighted difference vector. So you can see the steps. What is the second step? First of all, first thing is choose the target vector. Okay, so therefore choose the, what is the first step here? Choose the target vector. I have written somewhere Okay. Okay, students, let us one by one. The first step is target vector, and then let us choose one target vector. Let us denote this as target vector xt, and then next thing is what is the second step? Choose two population members and denote as xa and xb. So remaining we are having 5 solution vectors. Let us denote randomly. Let us choose this as xa, and let us choose this as xb. So after choosing this, third step is build the weighted difference vector. Okay, build the weighted difference vector between xa and xb. Weighted difference between vector xa and xb. So we have already denoted this S2 as xa and S4 as xb. So let us write like that only. xa is 0.92, 0.92 and 0.33. This is x1, x2 value, x3 value. Similarly, you take xb vector. In our case, it is a solution 4, 0.12 and 0.09, 0.05. So for these two vectors, perform the weighted difference. So first calculate the difference vector. So difference vector, let us denote. Calculate the difference 0.80, 0.83, 0.28 and multiply with some weighted value. Let us take in our example as 0.80. So if you take, you will get the weighted difference vector. Okay, so finally we will get, if you multiply 0.8 with each of the value, you will get weighted difference vector. So that is a step 4 we are doing. 0.66, 0.22. Okay, so that is so we have completed step 3. Next step is choose a random vector xc and add it to the weighted difference vector. So let us choose another vector in our table and denote as xc. So by randomly, let us suppose you take this as xc. Let us add to this step. This is step 3. For your illustration, I have done step 3. Next is step 4. So we have already selected S6 as weighted difference vector x1, x2, x3. First of all, write all the values. You select randomly vector xc. In this case, it is S6, 0.94, 0.63, 0.13. And the output of step 4 we will call it as a noisy random vector. If you add it, you will get 1.58, 1.29, 0.35. So again, let us go to the step 4. So we have performed the step 4. In step 5, we have to perform the crossover operation. let us see how step 5 operation is performed. You take the target vector xt, x1, x2, x3. We have already designated as the first vector as target vector 0.89, 0.04. You take this vector, solution vector, and then you take the noisy random vector, which is the output of step 4. So we got 1.58. You can see this 1.58, 1.29, 0.35. So that is the output of step 4. 1.29, 0.35. So now we have to perform the crossover operator. Apply the crossover operation. Okay. To get the trial vector. This is your trial vector x trial. So for performing crossover operation, you have to define a probability, crossover probability CR. Okay, CR is defined as, let us say, it is just a probability value. You have to define between 0 to 1. So let us suppose I define as 0.5. So as per this probability value, you choose any one of the value between target vector and noisy random vector. Okay, so as per this probability value, for a first variable, you randomly select any one of the value. So let us say I select this one. So again, you have to take 0.8, you have to select any one in between 0.89 and 1.29. So each is having equal probabilities as per the crossover probability. So again, I am randomly selecting this one for your illustration, 0.89. So you can simply think as a tossing the coin. Tossing the coin will lead to head or tails. If it is head, you select target vector value. If it is tails, you select noisy random value. So you have to perform this sampling for each variable. So for the third variable, I am selecting this one. So you can select anything. Say for example, I got head in the toss, so I selected the target vector. So this is your target trial vector. Now what you have to do is, what is the step 5? In step 6, we have completed the crossover operation. In step 6, we have to compare the fitness value and choose the best vector and store it in the new population. Now step 6, you have to, so we got target vector and trial vector, and we have already defined the function f of x function, x1 plus x2 plus x3. So we are already so we are going for minimization problem actually. Let us evaluate the fitness value of target vector. So by using this, we already know that target vector is 0.68, 0.89, 0.04. So if you perform the simple addition, you will get something like this. What is the addition value? Let us take one calc C, and you can add 0.68, plus 0.89 plus 0.04. So you got 1.61. Similarly, the fitness value of trial vector is here. This is the trial vector. You can see this. So let us calculate the trial vector. 1.58 plus 0.89 plus 0.04. So you got 2.51. Since it is a minimization problem, you have to choose the vector which is having less fitness value. So you have to choose this one. This is the minimum value. Here our objective is to find minimization. Okay. So you have to choose this one. So corresponding to this, in between xt and x target and x try, you have to select this one. So xt is the best solution. So you have to store it in the next population. Store in the next population. New population or next population. So what we will do means, while constructing, this is a new population. While constructing the new population, you store the first solution vector S1 as 0.68, 0.89, 0.04. So that is a first member in the new population. Similarly, you have to find S2, S3, S4 by S5 and S6, because the population size is 6. So you have to repeat the steps whatever we performed. All the 1 to 6 steps you have to perform again. Now this time in the next iteration, you have to take S2 as a target vector and randomly choose XA, XB, XC and apply mutation and crossover respectively to get new member. So likewise, for each target vector, you have to repeat all the steps, step 2 to step 6. So in this way, you generate solutions in the next population. Okay. So finally, we will write the algorithm. We will write the differential evolution algorithm. First one is inputs. For this algorithm, the inputs are fitness function and control list parameters. So control list parameter means you can define maximum number of iterations and hyperparameter, crossover probability and uniform distribution functions, all these things. So the first step is initialization. Let us write neatly initialization of all the population, first population. You can select the best solution from the current population with the help of fitness value. You can initialize the loop variable and you start the looping statements while not termination criteria of population F, C and I. And for each individual, here you need to select each individual as a target vector and evaluate, decide whether it has to be replaced or not in the new population. So you have to select each member in the population as a target vector. So that's why you have to use this statement for each individual S belonging to P. So perform S dash. Here you need to perform the mutation. We have already defined how mutation can be carried out in the previous slides. You can see these are all mutation only. These are all step 3 and step 4, you can call it as a mutation. Okay, step 3 and step 4, you can call it as a mutation. And then you need to check if f of s dash is less than f of s, then whether the new solution is better than this, means you can perform replace in the given population. You can perform indef in the 9th statement, in the 10th statement, in the 10th statement. So what are the steps we have defined? We are neatly writing in the form of algorithm. Again, you can check if f of s dash is less than f of best solution, then just we are checking whether the solution is best or not. This is for displaying the output. Other than that, this statement is not necessary. Okay, and you can end the if statement. Just we are storing the best solutions in the B. So finally you can end the for loop, end the for loop. After that you can iterate or increment the loop variable, and finally you can stop the while loop. Once termination criteria is reached, you can stop the things, and finally you can output. So you can output the last population P, or you can output the B. Okay, that is it. Actually here you can add another statement also, mutation, and also you can perform crossover also, mutation, and you can add crossover also. You can add this statement also. That is not a problem, because we didn't mention earlier. In this way we can perform optimization using differential evolution algorithm. The only thing you need to understand is how mutation crossover is happening in differential evolution algorithm and how optimization is achieved. So in the criteria, in the control list C, you can define different parameters like maximum number of iterations, uniform distribution. What is a distribution function you have to use for initialization of population, and the crossover probability, that also you can define. Crossover probability also you can define. So these three things you can define in the control list parameter. Okay, I hope it is understand. Thank you, students. You can note it down. So this is a basic version of differential evolution algorithm. You can also perform various improvisations to it to perform a good optimization algorithm. Thank you, students.